all the streaming, the best place is on the edge of technische for the streaming. So you are going to stand here, and you are standing behind them.
Right.
Yeah. When you have received your diploma, the laudation will come still. But I ask the audience to sit down but you remain standing. And then after the laudation, I don't know if there is one committee member online.
I don't know either. It's not planned like that, but it could happen.
If it is like that, we after everything is over, we take a picture there, and then we take pictures with the steps. And first with the violin, and then with your mother and your wife. Then is everything over. You two will take all the stuff out of this room, and you are invited to go to the reception room. I take the committee to Ontario, and they are the first one to congratulate you. I take them later to the, yeah? I will take a booklet so that can be signed by the committee members. Yeah, is that clear?
Yeah, I think so.
If you have questions, yeah. Yeah, it's clear for you too.
Yeah.
So you always walk behind it.
Yeah.
Don't make fine.
And good luck and no yes.
Okay, let's get started because I made it a bit too long and I was asked to make it like twice as short somehow. Probably not going to be possible, so embrace yourself. I wanted to make this slide deck a bit of a Jin way. If you've been to presentation of Jin, he looked back into his years at TU Delft. And of course, there's a research to it, but also there's some live into it. So I would like to have a chance to talk about the research I made into my hard drive, searching for the photographs I made during the last 4 to 5 years, and try to make it like a storyline and timeline of what it was for me in the last 5 years. That takes me as early as getting back to interview process and how I get to know about TU Delft. It might sound a bit scary, social condition in part, but it's nothing else but just trying to integrate and come into the new society, being an international student. I also want to speak about the Netherlands and developing warm feelings towards this country. So that includes of relocation, work-life balance, and just reminiscing about all the good times I had. And then I wrap it up with some selected papers from my research. And it's for all of us, starts with this diagram, or at least the graduate school once showed you this diagram where you're supposed to finish your PhD journey in 4 years. For me, it took a bit more than 4 years, but the main part that you go through is a lot of changes, and you need to adjust to them. At least this is a journey of my chair. That means that a good indication for new students especially that you'll probably be doing a lot of this sit-up work, a lot of hours in the office, but at one point you can make it up to this desk. And with this red arrow, I show a bit of a timeline. So then before even starting this program, I was back then at my second master degree, enjoying nice views in Norway. And I find it very funny that with a friend of mine, Alexander, we were drinking this Heineken. So that's a good indication and link to the Netherlands already back then. And then I was enjoying food and enjoying a lot of field trips, including this whale steak at top right. And I was then also enjoying and not enjoying having distant relationship with my girlfriend back then, but now wife. But we still persevered through this. At some point, I thought I better start looking for a job so I can reconnect. And like 2 places, I ended up final round was in Chalmers, Sweden, for a project that is quite linked to my degree, and other project here in TU Delft. And something I wanted to point out there at TU Delft for interview, I was wearing formal shoes. And for my Chalmers interview, I was wearing these white sneakers, so probably that's why I was hired eventually in the TU Delft. And today I'm also wearing formal, so make some conclusions about that. Then this picture is literally from the day I got interviewed in Delft, and I fell in love. You can see how beautiful the city is, and you can see that, yeah, you saw it for yourself. In the spring, it's extremely nice. And then it took probably 1 year to get the papers running, and then I could get hired. So then I'm on my first year, or I should say this 1.5 years, where everything is still a bit slow and stretched, and you have time to enjoy the surroundings. At the end of these timelines, it gets a bit more compressed and a bit more hectic. But of course, it's all still linked to some changes you're going through. It's international environment. It's cultural. You can even say stylistic. At some point, you might start be wearing clothing that the Dutch people wear it, and so on and so forth. And some adaptations you need to go through. And of course, there is known concepts from psychology, or even a quote there from communism, that your environment affects you, and there is some kind of a feedback loop. And on the B diagram, you even know that your brain can affect your heart system and your gastrointestinal tract. So that's what you call a gut feeling. But the idea here is, of course, your environment affects you somehow, and you need to adapt. So what I wanted to talk about here is this really first year environment, and I would like to admire at this point people who were there back then, but also in the future. And I would like to give a single quote that I associate with this person, or maybe just give a compact impression of this person as I had it back then. So start with Roland, he's still here. Hi, Roland. He goes with goedenavond early at the morning. At least when my day starts, he already goes goedenavond. Apparently, that means good. What's that? A good afternoon, because he was already early at work, starting from 7. Then with Paul Urbach, second picture. For those of you who don't know, is also starting very early, but a quote I would remember, he would always say, "You're a physicist, you should find an answer." So that's an example of person you get inspired from, because he doesn't accept the answers I don't know. And well, perhaps there will be answers like that from that today from me. For Sevani, I would like to give it credit for her persistent and reminding me that sometimes measurements in the lab can be just repeated long enough, and it actually works. Repeating some measurement can lead you to a better measurement, and that's what you should rely on. I would speak about Wim, because his quote is, "Maybe we could patent that," and he also asked me to patent something during the PhD. I would always recall him as a very organized person, and some of you might also recognize it, so that's very inspiring and helped me a lot actually to write this patent back then, to get my writing more organized. So second person there, not everyone is familiar with him, but Rob Mude, he works at some high position in TU Delft, but he was also at my graduate school interview stage, or not interview, at the course at the graduate school, were completely taken out of context, but he sometimes finds himself in TS reading the papers he have to read. And for me, it's like example of overachiever person, that he puts a lot of dedication, and at this point we also can recognize he is high in TU Delft. I would also like to acknowledge Joseph, perhaps he's watching online, and he's probably the smartest person in the group. You can argue with that, I guess, but to me he was, while he still was visiting. And for me the quote is, he would always say, "I'm not sure what this paper, actually opposite, he's not sure, but he perhaps can always give you a link to a paper, the year it was published," and he had really encyclopedic knowledge about everything. I would go for Stefan Baumer at the top, for acknowledging him for actually pushing TNO to do things, so that the delays I encountered, they are not 3 years, but only 1 year. Then I would acknowledge Tim for teaching me how to operate in lab, and making sure I'm not looking straight into the laser. So I'm quite thankful to Tim. And I would acknowledge Jeff for his timeless but, which basically, for those of you who don't know, he's a very critical person, and he never accepts any answer without disagreeing with it first. I would like to acknowledge Omar Gavhari, especially first year. I would remember him walking around and talking about probability experiments and in general metrology. Buffon needle experiment, I think, was then his favorite thing. And in general, he's very passionate about science, so that also transmits toward people around him. I would speak about Aurel as a persistent defender of the macros, but basically any novelty that comes into the group, he's always involved in. I would like to acknowledge Yvonne for this timeless phrase, "Nog een dag in paradise." She would probably say it every day or every 2 days, meaning that she's enjoying life a lot, and she always created a really nice atmosphere in the group, so I enjoy it a lot. Felipe and his phrase, it's only going to get worse, he said. He was partially true, speaking about how the tension rises towards the end of your PhD. But since Felipe persevered, so can I. And since I cannot cover everyone, I address all the PhDs, postdocs, bachelors, being here or watching online. Just please look into the acknowledgement section of my thesis for that matter. And this is some Photoshop, which I might print out for later on, including some older generation of PhDs, postdocs, bachelor, and master students, but also a newer generation. And there is some, of course, linked to the art there. Okay, maybe go quick about this so we can save up on the time. I wanted to say that another part of environment that shapes you is also the place you live. I happen to live always in Delft, most of the times with Duo. I didn't have to move around, so I could always take a good sleep in the morning and be more or less on time, not before Roland, of course, be at work on time. I lived this Balthazar place, Balthazar van de Poel, I lived rond Holsland, Mijnbouwstraat, Oude Delft. Dmytro is one of my favorites, and I really envy because one of my parents is also now living there. It's a super nice place. If you get a chance, just go to Duva and convince them to give you this stuff. But why I'm even saying this, I want to say to a new PhD generation is just own the place. Don't treat it as if, you are just temporarily here, so there's no reason to get attached. I truly believe that you actually should try to get attached because it will help your determination also finishing your own PhD project and just it'd be better for your mental health. And there are some examples of me just enjoying the place as well, even buying Christmas tree, and that's quite a commitment. Really quickly, something that my parents laugh about is my eco project I made moving from main Delft to outer Delft is instead of renting the car, right, I bought with my wife just this trolley, and we moved in 15 iterations during 3 days, just moving boxes from one place to another, and I'm particularly proud of that. So moving these boxes, I could make my last place I live now, it's super tiny, but I could make it again cozy, and it's maybe a bit dirty, so but I could even buy myself an oven so I can enjoy my living better. Continuing on this wave of this life balance, life and work balance, for today at least, I would like to pretend there's more life to it than work. So this guy, and I would speak about some experiences that for you as a PhD can make your living a bit easier, can make your a bit distracted from this stress of doing work, or being under the deadlines and so on. So for me that was museum card that offers you in general 450 museums, where I went more like 5-10 museums, but 3 to 8 times, so 80 times I went to places like Rijksmuseum, Boijmans Verbunnen, and many others. So then you can also get married during the PhD, and you can also help someone to get married. And here I say hello to Alexander and Dasha. Marrying friends, Dutch food, that's another topic to enjoy and to get distracted from your research, as repulsive as it might get in the first place. Things like haring or, I don't know, maybe for some people oysters. Over the years I started enjoying this a lot, and my personal favorite is on the right, like this gehaktebal with mayo. So I recommend to try this. Oh, trying food made me gaining and losing weight, mostly gaining weight, but it's not a big deal. I can live with it, but you should also be aware of that. So first year of my PhD, I gained 10 kilograms from this switching from somehow, probably before was more active, and then switching to a sitting job, I gained 10 kilos, and this right picture, I probably already, I don't know, -2. You can also enjoy beers, and I did that. You can have 1 or 2 beers in your free time after the work, and there are many types of beers you can enjoy. You can also go to Belgium to enjoy even more. Animals, we didn't get to own the animal at the rental, so that's a big pity. But you can, there's a goat over there. So I can also relax a bit and, just get distracted. So your university life, and I should say that like recent time for me, it's less social because I'm less, stressed or so. But especially in the beginning, I was enjoying a lot going to the coffee breaks or having the events online. And I really encourage, especially like new PhDs, to keep this tradition if possible. So join the coffee breaks and try to get to know other people. And this one is also going to conferences. This is an example there. I did hobbies, and if you want, you can go to Pappenstraat and see these clay products. And I also participated in making one of them, making these 2 houses, and they're now part of the Delft city. You can go Efteling, you can go many other attractions and museums, as I said before. You can also, don't forget your families if you're international students. They will help you to regain the flow, recharge, and just keep you happier in general. So I met both my families, and of course I met friends. So I invited them to Netherlands. I showed them how it is. I went abroad, I should say, to also meet them. And I should say I also miss them quite a lot, so I say hello to them watching. PhD journey is almost over by then, so you already spent so much time enjoying your life and maybe also doing work, and then you're here, and that's the part where I do formal layman talk to speak about what kind of research I've been going through. And this is most simply, I hope, explained through this pipeline, which is common, where there's a journey of the wafer ingot from ingot, to the chip. And there are many iterations through which this chip or silicon wafer you see on the right is going through. We are working at metrology and inspection of these substrates, or in the future we'll be looking at also pattern surfaces. The idea, these tiny bright spots, they are not so big as in the picture, but we are trying to look in the contamination that is landed on these wafers. We're trying to inspect it and trying to, well, give some information about location and size distributions. This happens in different scenarios in general. They could be bare wafers, or they can be patterned and rough surfaces, or it could be mask blends, etc., and a pellicle. And so this is a whole overview of what is possible. My whole thesis is really just this guy, in trying to look for smaller contamination. There are some techniques available that are all well known, where we belong to actually category B, where we measure both reflected and scattered light as compared to SEM or dark field, to other microscopes that can do contamination detection. And the moment I joined the project was 2017. There would be a single beam CFS, still single beam, but we're working on that. And the sensitivity back then was about 100 nanometers, and it would also take a lot of time to scan the surface. So even though there's been a lot of effort, a lot of work put in to challenge this number, by the year 2021 or 2022, we would still be behind, but that's fine. We are also in university technique, and perhaps we are still to discover the niche for this technique later on. I produced some papers, I produced some research that can be put broadly in categories as the data processing pipelines, and can be put in categories as the methodology and hardware improvements or hardware applications to the technique. Among them, bottom two would lead to increasing the sensitivity, such as noise filtering or some methods to define the focal position. We could end up with the help of also Iman fabricating some validation samples that we can show that we can go lower in sensitivity, even down to 30 nanometers, so from 100 to 30 nanometers. Other thing which is at least was acknowledged by the publishing house is applying machine learning techniques. Yeah, it's a buzzword, of course, but applying the post-process techniques to the data sets, because we went from smaller scale to medium-sized scale of the amount of data we have to analyze. And for this, I did it more old-school way, but also I tried to do it more new, fashionable way with convolutional neural networks. That's really just two similar things. One is from past, and other from more novel approaches. For this one, what particularly was remarked by the editors of the journals, they like the part that we can address open set classification kind of scope. So where this contamination that I talked about in the beginning, what if there is something else other than we expect to be there? So then there is a supervision of the output layers, and then can be done to treat that. And that ended up, as I said, with this spotlight. So that's probably the highlight. But otherwise, I'm, of course, proud of every paper I've been involved in. So thanks a lot for the attention. Should be seated there.
Ik open de zitting van de commissie ter beoordeling van het proefschrift en stellingen van Dmytro Kolenov, Master in Radiophysics and Electronics. De verdediging zal in het Engels worden gevoerd. I request the promovendus to go to the lectern together with his paronyms. A warm welcome for all of you at the public defense by the candidate of the dissertation entitled Coherent Fourier Spectrometry for Sensitive Detection of Sub-Wavelength Structures and Particles. The Board for Doctorates of TU Delft has installed a committee to evaluate the thesis propositions. The committee will have a debate with the candidate in the public, and it's an honor to present the members for this committee, to whom I extend a hearty welcome. First of all, closest to the public, opposite to me, Professor Hofmann, Ruhr-Universität Bochum, Germany. Next, Professor Den Boef, VU Amsterdam and ASML. Then, third, Dr. van der Wallen, TNO. And finally, Professor Koene, Delft University of Technology and ASML. At my left-hand side, Professor Stallinga, Delft University of Technology. And at my right-hand side, Dr. Pereira, promoter, Delft University of Technology. Thank you all for taking part in this academic ceremony. My name is Witteveen, and it's my pleasure to act as chairman on behalf of the Rector Magnificus. Now, I would like to start the opposition and give the floor to Professor Hofmann.
Vade promovendus. First of all, it was really a pleasure to read your thesis, a very impressive work. And I would like to start with a more general question about the robustness of your results concerning nanoparticle detection. So you started with well-known particle material and sizes. What happens if this changes? So if you have different materials, for example.
Hooggeleerde opponent, thank you for your question. In this question, or in this answer, I should address different particle types, and I guess also should say about combination with the sample, and how is the results I display are generalizable, right? So I would say that in the core of this thesis, we would present results for detection of polystyrene particle on silicon operating at visible wavelengths. In this scenario, we actually have quite a good contrast between contamination, so this spherical particle, and the substrate, so it's somewhere, refractive index for blue wavelengths is 1.5 for a particle, and real part is 5.4 for silicon. So that means whenever we would face lesser contrast, we would not be able to establish same sensitivity limit as we established for this particular scenario, given the same setup, given same wavelengths, or given same input. On the contrast to this scenario, if there would be a higher contrast between the particle and the surface, then we can move towards even smaller detection. That would be my assumption. In terms of materials selectivity, the underlying choice for having this kind of material is to make it low scatterer, and where scattering is proportional to the permittivity of this particle. And this is by design, whereas if we were to put it as whether CFS can be used as material determination technique, then there's something I can comment on. However, in general, only accessible via calibration and via introduction of more of the input parameters, such as change in wavelengths or input angle. So the general scope is, of course, if the scattering cross-section means high permittivity of this particle goes into the high number, then there probably would be no reason to not detect it with this technique.
What if you have, say, dust particles, so you have a mixture of different materials? Is there any way to use your concepts?
I tried to address this a bit in the outlook of the thesis, where for the future I would really like to answer this question myself, whether we can quantize core layer of composite core shell particles. So in this case, we would model this as a particle for dipole, and dipole moment would be defined through polarizability and the input field, and the polarizability according to, like, you can find in plasmonic books in literature and many other places, you can find definition of the polarizability through core shell way, or actually multiple core and so on. So that what is the key there? You would still need to have some prior information, because since your then input field is proportional, your dipole moment is proportional to the input field, and then this term of the polarizability includes radius of the core and radius of the shell. That means you at least need to know the core size to be able to say what is this added value of composite core shell particles. And then I also speak about, and I actually had to do this, concept of, not a concept, just estimate formula of lattice sphere equivalent, where we say gold particle of the smaller size is lattice sphere equivalent of lower index particle of the bigger size. So a similar concept would be with different materials of the composites. It's generally not so easy to say if it's bigger contamination of lower index, or if it's smaller contamination of the higher index, or there's some modifications to it.
What about the shape of the particles and the ability to distinguish particles from scratches on the surface?
Scratches, and I would try to address this in parts. So one is shape. I need to say, put a note here. Shape and edit versus defect. So it should be possible to display this even from ray tracing perspective. So first I try to speak about defect scratches versus added contamination. So when we can generate sort of signals that we have, which is balanced opposite polarity plus and minus differential intensity. As actually we do it in voltage domain, but there are some critical positions of the probe versus this scatterer, where we say if it's perfectly in the middle, there's a symmetric scattering, so differential signal would render you 0 value. And if just two rays hitting particle that way, well, then probably you can still get just symmetric 2 dots on your detector. And if you offset this left or right, there will be in asymmetry in refraction from this added particle. And if we were to have an exclusion from the surface, also I hope I can draw this somehow, but we see this experimentally, at least for sure. That still doesn't answer, so it has to be offset a bit. So one ray is coming like this, and then it perhaps goes this way, and then one array is getting here, goes that way. So there we would actually see something like asymmetry, but also there will be more light in one of the halves, which eventually would render signals of opposite polarity. That's our take on defect versus added contamination. In fact, even though we don't really look so much into defects in these theses, but prior research of PhD Sarati Roy on this project demonstrated defects in the OLED samples. So there will be holes introduced there, and that we could also identify in the presence of reasonable roughness. And your second part of the question was?
The shape.
Regarding the shape, to me is probably the most complex one, because very conservative take on the shape is that we are aiming at deeply or sub-wavelength regime of particles. For this regime, regardless of whether they are free space on it or in the surface, you get a dipolar or dipolar modified radiation diagram. So for the surface, it's something like this. What does that mean? If the particle is sub-wavelength, then doesn't matter the shape, it will probably produce same radiation pattern. And there's then no changes over the pupil in terms of directivity. It's only the magnitude of the scattered field that can be monitored. But good news, it doesn't mean that we still cannot try to calibrate this. And the way I would approach this is having particles, perhaps different aspect ratio, or indeed we know for sure by fabrication that they are different shape, and trying to scan them into orthogonal directions with high raster scan sampling, so we can establish whether there is something interesting coming in from there. So then, to put it short, the interaction of the probe and different shape should at least give me different kind of blob in 2D. So the signals that we get, they are now should basically fit inside of the circle, because with the SSVs we're interacting with. But if there is some different shape, then perhaps this pattern is not anymore something that you can fit in circle, to put it very simple.
And the final point concerning this part, what about aggregates of particles? Mm-hmm. Can you distinguish aggregates from more complex shapes of single particles?
So my take on this would be, the way I think about it is our system would be far field detection of reflected beams. So I discontinuity here, and then there's just some surface interaction. Then, of course, some people left minus right. What we can do as well is do left plus right. What is then the scope of microscope? There's probably just single pixel, and the light is getting focused. And there were before same collimated line entering from that side. And then there may be even confocal microscope that filters out the fraction of the defocused light, if there is some volumetric samples. So that there's a cancellation due to this pupil filter. So we know that from resolution limit, microscope will give you lambda over 2 NA. Confocal would, so that's 0.5 NA. Lambda over NA. This guy will give you, so confocal microscope would give you 0.47 lambda over NA. Then I would say, in principle, between these two in the middle, there's no loss of information. There just was a lens put there in between. So I would say integrated would still be at 0.5 lambda over NA. And then there is this differential mode, which is known to cancel laser intensity noise fluctuation, or cancel common signals. So that's like two main selling points for our technique as versus regular microscope. That reduces the noise, and that's a bit outside the thesis, but for the metrology target that we already had the chance to look at, we might do a bit of a confocal microscope scale, or maybe just a little bit better than that. So I would unconfirmed say 0.4 lambda over NA. So that means when we visit the sample and there is aggregates of particles, would we still be in XY plane limited by the diffraction, and would not tell apart really easily if it's two or one particle. Only hope there is similarly to what I described here, by prioritizing this a lot and calibrating out how the this volume of interaction looks like as compared to one particle, for instance. This we can do. We can say that aggregate of two particles or three is definitely different from one single particle of that kind.
Professor Hofman, can I ask you a question? Are you satisfied with the answers provided by the candidate?
Yes, I am.
Thank you very much for your position. And I would like to continue with Professor Den Boef.
Thank you, Mr. Chairman. Waarde promovendus, I've read your thesis with big interest because, as you know, particle detection is very relevant for the semiconductor industry. It has already been very thoroughly studied in many places in the world, yet you managed to add really new insight and new ideas and new creativity to this very complex yet relevant topic. What I particularly appreciated is the width of what you covered. It is not only hardware, but you also addressed machine learning techniques, also the modeling, which makes it quite a comprehensive work. But after reading through all your chapters, I was left with two topics that I would like to discuss with you in a bit more detail. The first topic concerns the heterodyne detection that you report in chapter 3. Heterodyne detection is well known in measurement techniques. You do show encouraging results, but I don't quite understand one part. You present the 2F mode, so the double frequency detection, but then you assume that there is a double frequency present in your signal. Mm. However, you apply a sinusoidal intensity modulation via the laser diode to your light source. Mm. And if the system is perfectly linear, then where is that second harmonic coming from?
Gogolir, the opponent, thank you for your question. The question relates to a second harmonic demodulation done in heterodyne. I think I should make a remark that actually I can do both. That I make a remark that we modulate our laser with square poles, not sinusoidal, but doesn't mean it can be done with sinusoidal. So I try to address this question in that manner.
But then a square, if it is a 50% duty cycle square, it would have only odd harmonics. So I'm still puzzled. Where is that 2F coming from?
So I maybe do a bit step back to make it a bit clearer. So we would have laser that is VF modulation, that is direct modulated by a certain frequency. So this goes into CFS. Then there's this detector signal, so photodiode that we would put as input one to the heterodyne is implemented with lock-in amplifier. Then we would have effectively our not input 2, because that can be also done within lock-in or can be done with external waveform synthesizer, but input 2 we would do F referencing, right? Yep. So then what I say is, in order to modulate the laser, you need to get it first into the lasing mode, and that is done with the DC component. So you need to offset laser with something like 600 millivolt to get the lasing going, and then you can modulate with the waveform on top of that in order to produce a traceable frequency. So come together, F mode is square poles. So that would be 0, and precisely what you said, 3F 5F, so on odd harmonics. So when this is being applied to a laser, you also, what you effectively do is you upconvert the signal of the particle that was present at the detector. So there will be now DC plus carrier, F plus carrier, right? And 3F plus carrier of the particle on top when we do upconversion. So there will be close to this modulated frequencies, also the frequency of the particle. So that's really close to this one. So F plus F particle, I would put it like that. So then I would demodulate this with 2F, right? So then I would mix. What I do as the output of mixing is then sum and difference of these bits. So that would give me 2F minus DC, 2F minus F, yeah. F, 3F minus 2F, it's also F. And yeah, so there will be more components like that. So what is, I believe what is done then in second harmonic decomposition is then you can again multiply this result with second harmonic decomposition. So you would end up having components also at DC, at F, and all these other parts of the signal that you had at the previous step. And this one is then modified by low pass. So that means in second harmonic, you really fold this particle signal very close to DC.
Yeah.
Yeah.
Okay. Thank you. Yeah. Yeah. For the sake of time, because I have a few more questions I would like to put forward, I'd like to move on to my other question. To build forward to that, you mentioned low-pass filtering. I couldn't read in your chapter what bandwidth you used after low-pass filtering.
It's Google the opponent. Thank you for your question. It's really worth addressing because it's indeed, I think, was confusion point for multiple committee members. Is that one using the person who uses lock-in amplifier has to be really careful in selecting the settings that you run with. As an example I addressed there is I filter out completely one of the particle size that was present on the sample. And that's, of course, the result of, in that case I showed is also like the power and the input range of the lock-in amplifier, but also low-pass filtering. So what was just tested out to not affect the shape of the signal drastically, so moving low-pass filter closer and closer to the DC would lose the details of the signal. But that's something that we don't want to do. Maybe I can also then speak about that a bit. But we would run at around 1,000 corner frequency hertz to keep this filter there. And then you can also, there are way too many parameters, in fact. You can also tweak roll off of this to go a bit sharper if needed.
Okay, thank you. Yeah. Then I'd like to move on to my next topic also for the sake of time. On chapter 5, you talk about focusing, how to find the best focus. You present some new ideas, but I'm also interested, how would your method compare to, let's say, alternative methods that were also around, like Foucault knife edge, or basically the kind of methods that could be used for optical recording, for example?
Yes. Hocholir, the opponent, so the question is to some way compare this proposed method with the existing methods. So that is also being done as part of this chapter, where I really put my focus on the strengths of what I'm proposing. The strengths of what I'm proposing in the sensitivity. So error focus correction is often using feedback loops to provide the active focus control. This is done via generating so-called S-curves where someone tries to sit on this position of Dmytro, which means there is no, that means that you are in focus. And this is achieved in Foucault method, knife edge method, or this very often achieved via astigmatism method. If there is an interest, we can maybe speak about that a bit, but the main part is what I'm trying to highlight is if you were to define the peak-to-peak of this signal, which is error signal to provide the feedback, and I'm also aware that we are not actually doing feedback, but that's perhaps somehow by extension. I don't have a clear idea about this now, but having this peak-to-peak, one can define the linear region of this curve. And if projected on z-axis, actually, this is z, if we go in and out of focus, this I compare to the relay range, and I claim some metric of having, I don't know, 3.7 relay ranges. So what is done then, I go for my literature study and try to, it actually took me quite some time, I try to find what are the published results out there that speak about the slope of this region. With that being said, there's of course some adaptations can be done. Like for instance, if I read into astigmatism method, it is said that the slope of the signal is defined by cylindrical power of the lens. So it doesn't necessarily mean if I review 3 papers, there will be not another paper in the coming years where someone uses this to introduce a higher sensitivity. And since I already highlighted the strengths of this, the drawback, or let's say the weak point, is what I comment on is low accuracy. It actually makes it perhaps not so applicable for certain problems. So I speak of submicron accuracy there.
Thank you. Professor De Boef, are you satisfied with the answers provided by the candidate?
I'm satisfied. Thank you.
Thank you very much for your position, and I would like to continue with Dr. van der Wallen.
Waarde promovendus, I've also read your thesis with great interest. As you know, at TNO we work on particle detection with competing technology. So for me it was very interesting to see this technology, and there are so many different ways to make it even more sensitive. You have covered a lot of different techniques to do that. My first question is about the classification on page 108. So you show a table for both methods, so the more conventional method and the neural network method, detailing which particle class is classified in which class. So if the classification is correct, everything is on the diagonal. What worries me the most is the classification of background as particles. So this would be false positive detections. Can you comment on that?
Particle detected as background. Yes, certainly. Zeer geleerde opponent, thank you for your question. And I'm asked to address the issue of why the classification software can actually produce a confusion between such a different things as a data set that contains signal, that is a particle image, and with such a data set that contains only background, right? So why that would be possible, and actually in both methods, right? And actually in CNN there is almost no confusion with background. So
yeah. And in the other method it's not shown in the table.
Yeah, yeah. But I probably should also address actually the image before, but I understand the question. This also a bit links to the final part of this paper, where I wanted to address, as I say, open set. It's just, again, just a buzzword for open set classification, just a buzzword for treating the confusing inputs to classifiers. So what happens in the, so this network is really doing closed set by default. That means there's fixed number of input types and there is a fixed number of output types. There is no open variability for the classifier to treat the things that are unknown. But for now, speaking about the background, what you basically would have is the scores of your output layer is shooting high for something that looks like particle in the favor of background, which in this case could be due to the fact of how softmax operate. That's the claim I would try to make here. So I think that would be possible when there is so-called penultimate layer, which is have an activation vector. Activation vector is just a number per class, right? And if it just happened to be that they are very similar probability, then I would say, even though we treat this with the supervisor layer, since they are all low probability, just happen to be that when you put this through combination of things like softmax and openmax, that the scores are re-evaluated such a way that there is one class shooting higher than the other. I would think that there's a possibility there. Otherwise, it of course then ties back to something that would be hard to explain and would be only possible to explain by really pinpointing this subset, because what this confusion matrix can do, you can come back to the data you had and you can really select the image back that caused this confusion, and then you can see what was the problem, including labeling of the training data set, which is done by me and my student who labeled this data, who selected which goes to which class.
Okay, so if you would apply your methods on a completely clean sample,
right,
what are the odds of actually detecting a particle where there's none?
So, zeer geleerde opponent, thank you for your question. Should I address here really the algorithm part then, right? Because CFS part is, we tend to think there are no clean surfaces. And there are always something that we would find there. So I guess the question is, what if I specifically pass just background classes, a whole batch of background classes to the network? Well, that's also part of this test there at the page. At the page 108.
Yeah,
no, 108 is actually this. When we do the comparison, I don't send background class at all, because chapter 6 approach is not used to treat that. So in chapter 6, we, with this pick and pick finding method, we really go for something that would stand out from the background. I haven't looked into classification of something that is having the envelope about of the same pick-to-pick level. But however, addressing your question in the image 7.3b, that's where we actually send background class specifically to CNN. And the resolution there is quite low, but it can do, for this matter, for this set, 85% in test accuracy.
Yeah, so that means that quite a lot of background is detected as a particle.
No, based on this confusion matrix, background detected as, maybe I can zoom this one. So this entry, 8.2, is then my confusion with 40, and this part of the data which is confused with 50. part of the data which is confused with 80, but most of them is on diagonal, as you mentioned in the beginning. So that's actually quite okay to treat this with CNN, but I haven't wrapped my hand around how to treat this with like more of a conventional approach.
In some applications, actually, the false positive rate is the most problematic. So you want to keep that as low as possible. So if you want to use your CNN in such an application, could you tune down the sensitivity somehow to reduce the false positive rate?
I think I need to kindly ask you to repeat like the core of the question. We are speaking about the sensitivity of.
So perhaps you should discard the 40 and 50 nanometer classifications because there's quite a large percentage of false detections in that bin.
Right. Yeah. Now I understand. Okay. So that's the, let's say, beauty of this confusion matrix approach. You also get to see false positives, and as I already mentioned before, you can come back and inspect the inputs that caused that. That's also valuable, which then brings you to retraining this network forever if you want.
Thank you.
Thank you.
Then my next question is on table 1.1, where you state that the CFS can scan a 200 millimeter wafer in 9 minutes.
Right.
With a footnote, given that the scanning velocity is 100 meters per second. So what would still need to be developed to achieve this 100 meters per second?
Yeah.
It's on page 6.
So this is a very inspiring footnote for future research, of course. However, at the moment, the present technology being tested at previous project, I should say, at 3 meters per second. So that's proved. Our typical scan speed, as I do it in the lab, is a fraction of a meter per second, 0.005 meter per second or so. To go there to 9 minutes, we would need to do a lot. One of the directions that is now studied in the group is multi-beam, where multi-beam is going n times the reference speed for every probe. But another one is shown in this picture. Again, it's we have to be looking around because people do this and they can rotate the scanning stages in spiral trajectories that can be done faster than in the raster scanning raster scanning mode. So that's another source of trying to go faster. Finally, not limited even to these two, is introduction of beam shaping. So introduction of either diffractive optical elements or just lenses to make to find a compromise between being able to detect multiple particles in one go. For instance, I'm having the idea which I heard from someone is to having pencil beams where you introduce cylindrical lens and you sweep across the surface, but then everything within the lens is also within one signal. So you have to introduce diversity there to be able to actually find the locations back. So that's at least these three directions are promising.
Okay.
Dr. van der Wallen, are you satisfied with the answers provided by the candidate?
Yes, meneer director.
Thank you very much for your position. And next, I would like to give the floor to Professor Koenen.
Waarde promovendus, I join my predecessors, my colleague here at the left-hand side, in congratulating you with your thesis, because it was a joy to read it. I want to start with a question on chapter 4, the evanescent wave amplification, and maybe you can show on the board here page 55 with figure 4.6. So there you can see the dependence on the thickness of the covering layer, so the extra layer that you put on the surface. And you see on the vertical scale, you see the scattered intensity, and that's a relatively smooth behavior, I would say, as a function of the covering layer thickness. But if you now go to, this is a 3D assessment, but you also have a 1D simulation assessment on page 47. And there you see, for instance, in figure D, you see a very peaked behavior, and based on that result of the Fresnel reflection coefficients, you have decided to choose your thickness at 21 nanometer for the titanium oxide at 405 nanometer of wavelength. So given the 3D simulations, is this analysis with the 1D really necessary? Because I see that one leads to a very specific thickness, and the other figure shows a relatively smooth behavior.
Right. Hooggeleerde opponent, thank you for your question. So there's a bit of the discrepancy being pointed out between the results as produced by 3D solver and 1D solvers, or maybe even not discrepancy, but the point has to be addressed there, why in one case we would get smooth behavior and in other there is a resonance behavior possible. I cannot address this without giving the scope first, and then I can, maybe it becomes clear why that would be possible. So the scope of this enhancement effect that we discuss is based on the multiple assumption, actually. So that is first one, that there is interaction of probe and a particle can produce evanescent waves. That is a scope of, let's say, introduction to nano-optics book or introduction to nanophotonics book. So that's assumption one. Then assumption two, these evanescent modes can be, so evanescent modes can be coupled and amplified. And they're really two different things, because in order to come from an air, which is medium of our detection, into the higher index medium, you have to be having some coupling mechanism, and there this particle becomes a mediator. So that's a second assumption. And I referred here to the scope of research done at Imperial College London, Anatoly Zayev's group, but there are many other people discussing this. So the second assumption, we can couple the light to the waveguide. So then third assumption is this effect in the waveguide can be amplified so that there will be rescattering of this evanescent wave by particle. And this is the drawing I show in the chapter. So if there is a decay towards medium number one, towards input, or sorry, so let's say there's a guided mode propagating this waveguide that can interact with the particle on top, so that gets rescattered. Based on the, now coming to the scope, based on the simulation, there will be some resonant behavior to the, also to the one of the polarization possible. That would give us a good idea of something being optimal or not. But in the real world situation, there's still a matter of whether this third assumption is maintained and to what degree, I would say.
Yeah, so you justify actually why the 3D simulation is the ultimate goal of for your estimate of your thickness. So because the rescattering of the evanescent waves by the particle, as you mentioned in the third point, is important. But are there also not other aspects of your 1D simulations that make it limited, because they are only considered for normal incidence, and what you actually have is a probe consisting of a decomposition of multiple plane waves at different angles of incidence. So what would that give in terms of the resonance that you see for the S-polarization behavior?
Gehoord de opponent, thank you for this clarifying question. So actually with 1D, right?
Yeah, 1D, yeah.
A ratio of my kx to kr, that's my x-axis there, would give me also angles that are different from normal. So this one is actually giving me some idea about propagating modes, that our modes less than 1, kx over kr, and
Yeah, but the input beam is normal.
yes.
You don't use, you use one direction of
Oh yeah,
incidence.
that's
and not a cone of incident
right,
directions.
right. There is no decomposition done in 3D.
Yeah.
In 3D, there's a pre-computed focused field that is injected into the model, into the focal plane. Yeah, that's also true.
And would that, what would that do with the resonance at this thickness of 21 nanometer?
At this point, I think I have limited evidence base in this thesis to make such a claim, but it would be fair study case to try to produce plane wave decomposition in 3D solver and monitoring what each separate plane wave is producing as the result of this interaction, and monitoring if there is indeed this rescattering, because that's something that I would like to show, but I failed to show this. I could not really capture like finite time FTDT method way, some coupling process there.
Okay. Meneer de Director, is there time for another short question?
If the question is really short and the candidate could behave accordingly, yes.
Okay, then let's go for it. So your CFS technique is very similar to tachography. It uses a coherent probe, it uses scanning, it uses far field detection. So even tachography is being used for defect detection, like in the Paul Scherrer Institute with the rescan technology. So when do you use CFS and when do you use tachography?
Gogeleerde opponent, thank you for your question. I'm invited to compare tachography and coherent free scatterometry for the aspect of contamination or defect detection. So first aspect of that to me, for tachography part, is I always keep in mind that there would be phase retrieval technique, and in that case, so we are saying that tachography can do phase defects. For that matter, in this thesis, CFS was not shown to recover the phase measurements. We always relied on intensity or differential intensity signals. However, as an extension of this research, I'm also being part of now, we could show, but so that's, we put question mark. However, we have combination of CFS and synthetic optical holography published this year. So there's still comparable kind of defect type or information that we can retrieve from two. Then in terms of capacity to address clusters and let's see, yeah, I would say a capacity to reduce clusters or provide some pinpointing accuracy. So that means to know well whether you are on the right coordinate. I would say that tachography, I would presume, cannot do better than CFS. So CFS is better there. And finally, also the matter of computational overhead. of tachography, relying on overlap of the probes being certain ratio, such as 60% or so, makes it, at least in terms of data process, very much slower than CFS.
Professor Kuna, are you satisfied with the answers provided by the candidate?
Yes, I'm satisfied. Thank you.
Thank you very much for your position, and I would like to move your position to this table and give the floor to Professor Stallinga.
Dank u wel, meneer de rector. So, waarde promovendus, I've been looking at your thesis also from the point of view of the field of optical data storage. Before that technology became extinct, people have spent quite some time to investigate optimal methods to extract information by scanning a spot across a surface. And one of the elements that is often used there is the use of a quadrant photodiode. Yet you use a split photodiode to extract your information. So could you comment on some pros and cons, and wouldn't it be better if we would replace your split diode by a quadrant photodiode?
Gogeleerde opponent, thank you for your question. The question is to address pros and cons of quadrant detector and coherent Fourier scatterometry. There, of course, I should mention that by the year 2014 to 2016 and so on, predecessors research on that topic, the quadrant detector was the starting point of this technique. And I would say the whole system is also sort of legacy system to optical data storage. It's where it's getting its roots. What was noticed is that thesis, that usage of quadrant detector is, of course, beneficial to provide better localization in 2D. So that would be, instead of just knowing very well where you are in X direction, that's where we settled for, and I also commented that. But you would also know very well where you are in Y direction by subtracting top and bottom parts of this quadrant detector, for that matter. Why we decided not to do this eventually is also in the consideration of trying to go faster in the future. So it is already sufficient to have certain sampling rate in Y that would start from 2 signals per contamination. So that is size dependent. So then you can already rely on these signals to be perhaps sufficiently different from false detection. So then perhaps you don't need any more many signals in Y.
You say perhaps, but I would say that if you have not only a signal in the scanning direction, but also in the orthogonal direction, you would retrieve more information. So perhaps you could tolerate a bit more noise, and hence you could scan faster. So which of the two would win then?
Okay. So whether we want to go, whether we are okay scanning slower but losing this localization perspective, right? Fundamentally, more data or some critical amount of data according to Nyquist, let's say, in Y direction, would be, of course, beneficial to increase the localization quality of these detections, right? Mm-hmm. And in terms of signal to noise, we would have to be worried about if there is a step mismatch between the limit size scatterer and what we actually do in between lines. So we would suffer from noise if we don't manage to hit the contamination in the center. That's intuition for that.
Okay, and what's actually limiting you in speed then?
For the speed matter is I give ad hoc number, right? So that's like not fundamentally, but if I know from experimentation that if I have interaction of my probe, which is about 700 nanometer or so, first minima, and then I have particle which is, let's say, 50 nanometers, and say I select the step which is 50 nanometers, my first expectation that I would get probably 12 signals. And what I say in the thesis, that's absolutely not true. Due to the signal-to-noise consideration, I probably just get 4. And I rather say that I would go for diameter of particle divided by delta y step to be my practical estimate of where there is enough signals there. And then I would say that this ratio, n lines and detections, has to be more or equal to 2. So that means given input sample at question, I would need to know what is the smallest size that I am aiming to detect. And then I would then accordingly select the scanning step size, having in mind that I need at least 2 signals to represent this smallest size.
Okay, thank you. Meneer de Rector, is there time for another question?
Yes, sure.
Okay, so I have a question about your simulations in chapter 3. So you make a big point of approximating your particle or your contamination as a dipole, yet you say that at some point you need numerical modeling, where, for example, in figure 2.9 you have you must take extraordinary measures in sampling density to model this very small particle. So I would argue perhaps it's a better idea if you simply take a marriage of the two, because your particles are always so small that you can always approximate them as a dipole, and at the very worst with a few low multipole orders, and use that and combine that with, let's say, finite element modeling or FTDD for the rest of the surroundings of the particle. Could you comment on if that would be an advantage or if it's no use?
Waarde promovendus, could you please give a brief but correct answer?
Googgelier, the opponent, thank you for your question. There is known methods of combining 3D modeling with analytical modeling, whereas the latest one is, of course, always acts as a reference to be to compute your relative error. What is possible is to compute analytically background input field and launch this into the mesh of 3D solver and then resolve this together. This would be useful is actually if we want to account for some intricate effects such as evanescent wave, which is we unfortunately cannot describe fully, or these effects taking place in plasmonics, some Purcell effect, etc. So there you would pre-compute the field and try to launch it in 3D and maybe ask it to interact with geometry, because this is the selling point of what is 3D FEM, for instance.
Okay, thank you.
Professor Stallinga, you are satisfied with the answers? Thank you very much for your position. And finally, I would like to give the floor to the promoter, Dr. Pereira.
The promovendus. I have already asked many questions over these years, and I would like to ask you about your vision, a global vision about the experiment. So if you have to start all over again, so you have your setup now, and what would you do different, and where you think there are like points of improvement in the setup?
Yes, Zirgelir, the promoter, the points of improvement are definitely, was also pointed out by some committee members, is towards making setup more stable. That's vibration reduction. My personal favorite would be to test partial coherence. And I also really like this SOH method that we talked about in order to provide the focal plane determination to be as part of every instrument.
Thank you, Madam Beadle. I request the promovendus to take his seat again together with his paranips. The committee will withdraw for further deliberation in the committee room. This session is adjourned. reopen the session and request the promovendus to stand in front of the committee to deliver the sparrows. Het College voor Promoties van de Technische Universiteit Delft, vertegenwoordigd door de hier aanwezige commissie, heeft na kennis te hebben genomen van die proefzichtstellingen na uw verdediging daarvan te hebben gehoord, en in achtneming van het bepaalde in de wet op het hoger onderwijs en wetenschappelijk onderzoek, besloten u de graad te verlenen van dokter. Ik verzoek de promotor, door het College voor Promoties als zodanig aangewezen, zich wel onder haar opgedragen taak te kwijten.
Uitkrachtig van de bevoegdheid bij de wet toegekend aan het College voor Promoties, verklaar ik namens dat college, hier vertegenwoordigd door de rectus magnificus en overige leden van de commissie, bij deze u, Dmytro Kolenov, te bevoordigen tot de dokter. En u alle rechten te verlenen welke aan de dokterstitel zijn verbonden. Ten bezijde hiervan overhandig ik u het diploma dat u het recht geeft de titel dokter te voeren. Ondertekend door de rectus magnificus en de promotoren. En voorzien van het zegel van de Technische Universiteit Delft.
It is the promoter's privilege to be the first to congratulate the young doctor. Dr. Pereira, the floor is yours.
Dear Dmytro, maybe I should call you Dr. Kolenov now, but I keep it Dmytro. Well, the first time we met was long ago when you came here for the interview for this PhD position. And there you were a young man and you did very well in the interview, and you convinced me that I could offer you this job. And then I thought, well, nice, you accepted, and we would begin with our project. But there was some problem, and that was that the partners did not agree yet with the consortium agreement, and that took much longer than I thought. I thought, well, maybe 1 or 2 months, but it was more and more. And it took so long that I thought, yeah, maybe he's not interested anymore in coming here. He'll find position somewhere else. But once in a while, he would send me an email. Do you know anything about the position? Or I would send an email, please be patient, we will get there. And finally, we got so far to have the consortium agreement. So we said, okay, now you may come, and we start our project. And unfortunately, because of this delay, you didn't have much overlap with the former promovendus. So we had to deal with alone, me and you, to start this project. But it was a pleasure to work with you these whole years. And I think you have not only performed really well what we supposed to do in the project, but you brought new insights, especially the machine learning and neural networks, which for me was quite a dark field. And yeah, we could do some work on this, and actually your paper, the first paper, machine learning, is really being recognized already in the literature by many citations. And further, I would say I was really happy not only having you as a PhD student, but as a person that really I can rely on. You never say no, you always do everything. And you're always willing to help everybody. You helped many students, you helped many PhD students, even postdocs to get acquainted with simulations or some things in the lab. So I'm really grateful for all you have done for the group, also for education, and be present there and be always a very pleasure person to talk to. And I know that since a few months you have really difficulties related to what is happening to your country, and I really admire your strength You're really a strong person to keep up and keep going. And I think this can give you also a very nice start for your career further than this. And finally, I'm happy that you are staying another time, a short time for postdocs, a few months more. And, but even after that, I wish you all the best. And today, yeah, you can celebrate and you can be proud of yourself, your family too, of what you have achieved. Congratulations.
Dr. Kolenov, you now have the right to use the title of doctor. And your doctorate means that society can rely on your judgment, that you act transparently, and that you independently communicate your results and the social relevance of your work. In other words, your doctorate implies academic integrity. I wish you much success with the new status, with the responsibilities that come with your new status, of course. And on behalf of the Board for Doctorates of TU Delft, I congratulate you and your family on earning your doctoral degree. Dr. Kolenov, you may return to your seat and please take your paradigms with you. Ladies and gentlemen, I thank you for your presence, and hereby I close this academic session.
Zijn er leuke foto's van jullie? Mooi.